All right, so I want to do the first three of them together, okay? Just got to pair my Apple Pencil. Oh, good. The Apple Pencil's low. Let's try the other one. Okay. So actually, let's do. Which one do I want to do? Let's just do magnesium chloride. We'll start with that one. So magnesium goes in the center. Why? Because there's fewer of them. How many electrons does magnesium start with, Avery? 12 is the number of protons, the number of valence electrons we get from the Roman numeral. So what's the Roman numeral on the top? 2. So it's going to start with 2 electrons. You can put them anywhere you want when you're making bonds. Then we're going to bond it to chlorine. And again, the reason of hybridization, the reason why we do hybridization is because it explains why magnesium bonds. Because when you look at it like that, Jackson, my electrons are paired. Magnesium shouldn't bond, but it does. It's kind of like that one friend where you're like, how did they get to that? How did they date that person? You know, they shouldn't be bonding, but they are, and you just kind of shake your head. But somehow it happened. All right. Kind of like Ariana Grande and Pete Davidson, right? They shouldn't bond, but somehow they did. All right. So, chlorine's going to follow the rule of 8. Magnesium follows the rule of 4. Our center atom is magnesium. And then, Tessa, how many atoms are bonded to magnesium? 2. There are no lone pairs. So I don't know if you remember, Emmanuel, this would be a lone pair. Okay, so 2 electrons like that, that would be a lone pair. But we don't have that. So that's 0. You add the 2 together to get the steric number. So you can either use the steric number or just memorize that the hybridization will be sp, because it has to add up to the steric number. So my hybridization is sp, and if you haven't already, on appendix G, this is the steric number over here. This side is the hybridization, and the hybridization is sp, sp2, sp3, sp3, D, sp3d2, and sp3d3. So on some people's appendix Gs, those were cut off. So if they're not on there, make sure you have them on there. So if I have a sp hybridization, I only have one option, and that is linear. Okay? So I know magnesium chloride is going to be linear. The shape is going to be a straight line. That's why it's called linear. And then you can build the molecule, or we'll see if this works. It may not work. I might have to. Sometimes this thing blocks me. Let's see if it's got the molecule one. Molecular shapes. So either you build the molecule, Caitlin, or you can go to FET Colorado and, Ruman, can you put your cell phone away, please, in your backpack? No, not there, in your backpack. There you go. You can build real molecules. So sometimes they're on here. I picked a lot of them. I don't see magnesium chloride in my real molecule list, but I can make a fake one by adding or taking away bonds. So here is magnesium chloride. 3 atoms. Do I have a lone pair on there? Does magnesium chloride have a lone pair? No. So I'm going to take that lone pair away. So either you build the molecule, or you can use this to build it CGI way. Is this thing symmetrical? Yes. And it will give me the molecular name, linear, right there if I wanted to. Now what happens to this molecule, Colton, yep, there you go. Put it in your backpack. There you go. If I add a lone pair, what does it do to my bond? It pushes them closer together. What would happen if I added another lone pair? Push them even closer together. Okay? So lone pairs push the atoms closer together, and it also, there's my bond angle. So if you wanted to know what happens to the bond angle, now it's down to 120. No, that's not right. It would actually be less than 120. It's not 120. Whoever programmed this is wrong. This is right. The bond angle here is 109.5. Nope, that's wrong too. It should be 104.5. Anyhow, you can do that or build a molecule. It's symmetrical, so it's going to be nonpolar. You always use appendix F and G unless you only have 2 atoms. So it's a little bit different when you have 2 atoms. So that's why we're saving hydrogen and potassium iodide. So let's just put this in your notebook. When you have 2 atoms, you use electronegativities to determine polarity. So if you have 3 atoms or more, use appendix F and G. If you have 2 atoms, you have to use Appendix O with the electronegativity table. And the rule is, if you're above 1.7, you're ionic. If you're between 1.7 and 0.4, you are polar covalent. If you're below 0.4, then you are non-polar covalent. This is equal sharing. This is unequal sharing. So ionic, one steals from the other. I guess the way I kind of look at this is like, relationships. It always comes back to relationships. So ionic, one person pays for the dinner, the tickets to prom, the flowers, and the limo. One person just does everything. That's ionic. Polar covalent is there's some sharing. One person pays for the limo and the tickets, one person pays for the dinner, but it's not equal. But there's some sharing going on. Whereas non-polar covalent is you add up the total cost and you divide by 2. Complete sharing, equal, okay? So if you have 2 atoms, like hydrogen, you got that down? So hydrogen has 2 electrons. One electron. One electron, one electron. Is it going to be ionic or covalent? Well, that's the electronegativity difference. So Emil, is that going to be ionic or covalent?
It would be covalent.
Yep, that little voice you heard was your conscience telling you the correct answer. So, yes, it's covalent, so we're sharing. Now the next question, Jackson, are we equally sharing or unequal sharing? So this puts us in it's 0, so that would put us in the nonpolar, equal sharing. So right away, I know that my molecule is nonpolar. When you only have 2 atoms, it must be named linear, right? 2 points make a line. If you have 2 atoms, it's impossible to be anything else but a line. The shape, loop like this. You can pick either hydrogen to be the central atom. It doesn't matter. You'll get the same answer whichever one you pick, okay? So when you have 2 atoms, it doesn't matter which one you pick. But we don't have a steric number and we don't have hybridization. If you go back and look at your notes, this is an S and an S overlap. No hybridization is needed, right? I have my S orbital and my S orbital, and they're overlapping each other. I still have a sigma bond, if you go back and look at your notes, but we don't need hybridization to explain that, okay? So that's why it's Na not applicable. What questions do you have before we do potassium iodide? Yep.
What if you say that those 2 atoms bonded to the central atom was one?
That would be my mistake. 1 atom bonded to the central atom. Thank you. All right, potassium iodide. Potassium has 1 electron, iodine has 7. I need to figure out if we are ionic or covalent. So I'm going to go to Appendix O. Potassium is 0.91 and iodine is 2.21. So 0.91 and 2.21. Take the difference, it's going to be 1.3. Because your conscience did such a good time the first time around, Emil, let's see what your conscience has to say to you now.
It's ionic.
Maybe your conscience took a vacation there. So to be ionic, you got to be above.
Polar.
You got to be above 1.7. So it's covalent, but is it equal sharing?
No.
No, it's unequal sharing. So we're in the polar covalent, which means then I know my molecule is polar. Only when you have 2 atoms, V and A, do you do the electronegativity to find the polarity, okay? The molecule must be linear. There is no SN number. It doesn't matter who you pick as the central atom. Okay? I'm just going to put Na here, Na, Na. It doesn't really matter. So this is why the molecule is polar. Iodine has 3 lone pairs of electrons. There's 1, there's 2, there's 3. Yeah. There is no steric number for this molecule. Because what we have is an s orbital overlapping with a p orbital. So we don't need hybridization to explain the bonding. So that's why I put Na, 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 and it doesn't matter what you pick as the central atom. Polar means opposites, right? The Earth is polar. It has a north pole and a south pole, okay? Batteries are polar. It has a positive and a negative terminal. So polar means you've got opposites. Non-polar means it's the same everywhere. So this is what I call the tiny spaceship test. If I get in a tiny spaceship and I approach hydrogen from that way, and I approach hydrogen from that way, it looks the same. But if I get in a tiny spaceship and I approach from this way, I see my potassium. But if I approach from this way, I see 3 lone pairs of electrons. Okay? What charge do electrons have? Negative. So I'm going to see a large cloud of negativity around the iodine. One side of the molecule looks different. And so we say the molecule is polar, and we put in a really kind of cool Greek letter here, lowercase delta. So we say this side is partial negative and that side is partial positive. So for 2 atoms, check the electronegativity. So when you look at the rest of these, where is it? Is a page missing? I think a page is missing from this lab. I think a page is missing. I'm gonna go run off a page for you. But if you encounter two atoms, you have to use the electronegativities. Some of these molecules do not follow the correct rules, and so I just want to make sure you know which rule to follow. Here, SO3, I want you to follow the rule of 8. Okay? On the central atom. When we jump to IF5, put 10 around the iodine. Xenon, it's not supposed to bond, huh? But it does. Do the rule of 12 around the xenon. Okay? The rest of them follow the rules. I'm going to go find the missing page, and I'll print that off for you. But the rest of the time you have to work, you'll get this done. Use pencil. I'll come around and I'll check out to make sure you're doing it correct. Any questions before I stop?